Today, we're going to talk about approximation methods, specifically a class of algorithms called Monte Carlo. So what Monte Carlo aims to do is use random numbers to solve deterministic problems. Does this by sampling the underlying and likely generally unknowable probability distribution. The problem that we're going to look at today as an example is that of the independent set for a given graph G made up of V vertices and E edges. So the independent set is a subset of vertices from V such that there is no edge in E connecting any of those vertices in the subset. The decision version of this problem asks, is there an independent set of size greater than or equal to some number K? So, the naive way, the initial thought to solve this problem is to test all possible configurations. The problem with this is that this grows exponentially with the number of vertices and becomes very difficult or impossible to do with any sort of relatively complex graph. So instead, we're going to employ Monte Carlo to sample these configurations, which boils down to basically guess and check. So how are we going to do this? We will write the pseudocode as follows. For every iteration, we will pick a vertex in V uniformly and randomly. Choose a V in V. And then from that, we will compare it to our independent set at time t. This gives us a few cases. If V is already in our independent set at time t, we will remove it. So our independent set at time t plus 1 is that independent set that we started with minus that vertex. If that vertex is not in our current independent set, we have two possible cases. If the union of our current independent set and that vertex V is valid in this case, meaning it does not add an edge that is in E, for a new independent set at time t plus 1 is simply that union. Or else, if it would add an edge in E, which we cannot do because it would violate the original independent set problem, we reject that move, and our independent set at time t plus 1 is equal to our independent set at time t that we started with. So it's easy to see, since we're just choosing a vertex randomly, that this whole process for every iteration can be executed in polynomial time. So now we will look at an example. All right, welcome back. So for our example here, I've drawn an empty sample graph. We're going to start with our independent set at time t equals 0 as just this empty set here. So going through a few iterations, we're going to choose a vertex randomly. We got this one. So we can see here that V is not in our current independent set and that the union is valid. So we will add that vertex to our independent set. Our next iteration down here, we have this one already chosen. we will choose another vertex randomly, we get this one. Again, not in our independent set, does not create an edge. We can add it. And we go to our next iteration, which we now have these two chosen. We go to add another. Say we choose this vertex here. That is a case right here. Our vertex is not in our current independent set, but adding it would create an edge here. So we can't do that. Our independent set at this t plus 1 just remains at the independent set that we started with at the beginning of the iteration. So the next iteration, we still have these two. And then we choose another vertex. Say we choose this vertex that we already have. That's in our set, so we simply remove it. This can go back and forth. All of these can be reversed since it is a probabilistic algorithm. It can get stuck adding and removing one vertex over and over again, but eventually you will get two sampling configurations that have a maximal number of vertices chosen. Meaning that we can no longer add a vertex here without creating an edge in our original graph G. So to plot this, it will look like this. If the y-axis is the number of vertices in our independent set at time t, and our x-axis is just our time t, our number of iterations, we can fluctuate but overall rise up and eventually reach this maximum. So this maximum here, we will compare to our original number k to see if there is an independent set of size greater than or equal to k. And this introduces the concept of a mixing time. So this time here it takes to reach the maximum that it fluctuates about is this mixing time. So that is one question. Another being how to generalize this process to more and more complicated probability distributions that are unknown for larger and larger graphs, larger problem spaces. So I'll now hand it off to Ilya to show you how to do that.
Okay, thanks, Sam. Now I'm going to try to generalize what we went over in the beginning, how to use random numbers to solve like hard problems, and generalize it to like any probability distribution you want. So right, our goal is to sample distributions. Ideally, we generate all these things, like Sam said, but there are an exponential number of them, and that's just inefficient. So what I'm going to introduce is Markov chain, stochastic dynamics. So a Markov chain, mathematically, kind of means that your configuration, so you're working in a space of configurations, which would be like independent set matches for our example. So this configuration at the next time is equal to some function of the past iteration and some number t. So c is a random number for that current time, and x of t is the configuration at time t, and you do something with this random number and this configuration to generate a new configuration. So a Markov chain just assumes that the next configuration only depends on the one directly previous to it. It has no notion of history. Okay, so noting that these configurations are actually not time dependent, just when they show up is time dependent, without loss of generality, we can just say this is just x prime, this is just x, this is some. So the time dependence really only comes from the order of the random numbers. So how do we relate x prime to x? So we begin with the joint probability distribution. So P joint for x prime and x is equal to some conditional probability times some marginal probability. Sorry, this supposed to be the time here, because the probability distribution changes. Cool. So where W of x prime, sum over x, is equal to 1, probability probabilities conserved, as well as probabilities are all positive numbers. Cool. Okay. Now we could write the marginal probability for configuration at probability t plus 1 by just summing the joint probabilities over x. So we're given just the probability of x prime. So inserting our expression for the joint probability, we get something that looks like this. This is a so-called master equation. This equation governs the dynamics of our stochastic process. Now, like Sam said, we have to ask ourselves the question, does this dynamics reach some sort of stationary distribution? Do we actually saturate and start fluctuating about our answer? And in other words, we're asking, does the limit as t goes to infinity of pt of x reach some equilibrium distribution? In other words, what we're asking is that, given this equation, if you have at time t, sometime t, an equilibrium distribution, will you get back the same distribution, but like a new configuration? So a sufficient condition for this is detailed balance. Which is really what detailed balance is saying that is a statement of reversibility. So this is equal to which again is just a statement of reversibility of your omega matrix. So if we plug, so now we can prove that there is a stationary distribution. So given some t, if p of t of x equals, then pt plus 1 of x prime equals the same. You just plug it into our master equation. Now, using our detailed balance condition, we see we could write this as this. Sum over x. Is over there. So this sum, right, has to go to 1. So we just get to the fact that pt plus 1 equals x prime. So the master equation does have a stationary distribution. Okay, so that's all well and good, but how do we satisfy this detailed balance condition? This introduces something called the Metropolis-Haskins algorithm. So Metropolis-Haskins says, like, this omega matrix governs all the dynamics. So why don't we factorize this, or split this up into two different probabilities, where one is a trial probability and the other is an acceptance probability. Now, we can choose to have the acceptance probability equal to the minimum of x prime, probability equilibrium, over t. this is a very powerful conclusion. Now, this can be shown to satisfy detailed balance, and to show that, can be easily understood. So if you make an assumption that T is symmetric, i.e. T of x prime, this is true, then it cancels in this thing, and you're just left with a simplified thing, which is just minimum 1, and the ratio of this probabilities. So what does this mean? This is actually very straightforward in the fact that, so our acceptance probability, what should this should be a number between 0 and 1, right, like all probabilities are. If probability of x prime is greater than probability of x, right, this is going to be a number greater than 1. That means x prime is more likely, so you accept it with a probability of 1. Since this is greater than 1, this is less, so the minimum will return 1. You accept that move every time. On the reverse side, if x is more probable than x prime, this will be a number less than 1, so this will be the minimum, you'll return that, and then what that states is that sometimes you could fluctuate into this new state that's less likely than the current state, but you could also just stay at the current state you are. And this adds kind of like a weight to the current configuration you are at. Okay, but this may seem kind of redundant because we talk about sampling this probability distribution, yet we have to calculate this probability distribution to use this kind of acceptance criteria. But in fact, because this is a ratio, and these are probabilities, you could write any probability for a given x as some sort of thing that depends on x, some sort of value that depends on x, and that sum over all other probable configurations, zx prime. This is a normalization constant for these unnormalized probabilities. Now, if you notice, this sum runs over every configuration. This is impossible to calculate if you have an exponentially growing sample space. However, this ratio, each of these is the same normalization condition, so this just reduces to the min of 1, and then the unnormalized probability of both of those states. Thus, without actually having access to the probability distribution, you could sample that probability distribution, which is a very incredible result. You could even sample probability distributions that have an infinite number, infinite dimension. This sum is infinite, yet you could still sample that distribution. This is a very powerful result and generalizes the algorithm Sam talked about to countless number of other problems, from computer science to statistical physics to even financial models. Now we're going to go back to Sam to talk about how you could reformulate the independent set problem we talked about earlier into a Metropolis-Hastings type algorithm.
All right, thanks, Ilya. So now, let's see how we can extend that Metropolis-Hastings algorithm to our independent set problem. If we have a graph G and our set of independent sets, omega, we can think of each independent set in omega as a map from our set of vertices V to 0 or 1, where f of V is 1 if V is in our independent set and 0 otherwise. Further, we can assign weights x0 and x1 to control the desirability of having V in our independent set or out of it. So then we're going to define our weights of each independent set to be the product over all vertices in V of these weights decided by f of V, our mapping from V to 0 or 1. So then we can sample according to these weights to get a probability measure on omega. Doing this, we will see that we approach a stationary distribution, call it pi, of our independent set equal to the sum of all other independent sets is prime in omega of these weights of is prime, all under the weight of our independent set I. And from this, we can sample that stationary distribution without actually having to calculate an intractable sum over all of our independent sets that grows exponentially complicated very quickly. So with this example, I hope you've seen how Monte Carlo approximation algorithms can be used to calculate a very difficult problem, something as simple as guess and check, something very naive, ends up working with a few clever tricks, goes to this stationary distribution, and solves very difficult problems. Any questions?